be doing for the upcoming midterm. All right, so let me just try and pull up the documents here. I need 7.5. HPLC standard analysis, and then we need the stuff from week 6. Last week was week 5, but just gonna go through it. And this one.
I understand the stuff from yesterday.
Yeah. So, no.
This is what immigrants calculate your point of view.
Then. You're seeing it.
And 99.75. So that's the OP, right? No, sorry.
And I'm struggling with them. That's yesterday.
Is this right?
This,
Sure, you did fine. You always do this. You will get 100. You will, I'm telling you. I just know I made a lot of silly mistakes here and
No.
there.
I can't find it. Never.
That's better than I
There.
did.
Finally, the lab manual from,
I did a lot of mistakes.
Thanks. Yes.
I can just. Okay, so those of you on Zoom, so everybody in here, can you guys hear me okay on Zoom? Can't hear me. Yeah, okay, great. All right, so it's all as soon as thing on here. Camera controls, we're just learning this thing about the label. This guy on. Turn on this turn. There we go. So we're going to be doing HPLC external standard analysis. It's a very brief introduction to it. Most of what we're going to be doing today is just math about HPLC external standard analysis. And I'm also going to go through, for the benefit of your lab this week, we're going to go through how to set up your method on the HPLC. It gets a little bit, I find a little bit hard to do when you're not looking at the machine yourself. But we'll go through it anyways, go through like the motions of how you'd set up your method on the HPLC. And then of course you guys have these slides available and you guys can bring those to your lab as well. And then of course you'll have your lab instructor to help you. All right, team. So external standard analysis. Have you guys done any standard curves in the labs yet? You guys done anything with like setting up a chromatogram, like doing 5 standards and then the samples? Have you guys done those yet? Anything like that? All right, well, that's what external standard is all about. So external standard means using a separate standard. Right, so it's a separate chemical that's similar to the one you're trying to analyze. It could be analyzing it and comparing it to your unknown. And external, of course, means it's on the outside. There are such things as internal standards, right, which means you put a standard inside your samples to allow it to be compared to what it should be. So an internal standard you might use if you're expecting to lose some of your sample. So you want to make sure that you make the internal standard signal should always be the same. So you can adjust your signal for your analyte to boost it upwards or downwards if it's too high or too low. Your internal standard tells you what it should be. We'll get into that later. So right now it's all about external standard. So how do we calibrate? How do we do external standard calibration and how we use it to analyze? And then how we're going to do a standard or external standard manually or automatically using ChemStation. A lot of the time, a lot of your lab professors will want you to do your calculations manually anyways, but in industry, you'll find the machine can set up a curve for you and give you concentrations all by itself. So you don't really need to do that, but manual stuff is good to verify. And you probably need to manually in order to validate your procedures. Oh, I apologize if I yawn a lot today. My kid got me up at 3:30 and I haven't had a chance to sleep again yet. Okay, so what is the goal? We want to confirm the identity of our analyte. So our qualitative confirmation will be the retention time match, as long as the conditions are the same. Right, so we can determine the identity. And then of course, we know the area under the peak. It should be proportional to the concentration. We can look at the area and we can tell how much we have in our sample. And there's a lovely chromatogram there for you. Just gonna check if anybody else has been admitted to the Zoom. Oh, look, oh, anybody else in there? Okay. I need to like set somebody up as like an administrator to like
Same way.
get into Zooms on my behalf. Okay. Where are we? So. All right, so yes, your analysis will be a form of comparison. You guys will have I guess he's making an example of a ruler. If you guys use a ruler in measuring things in real life, it will have been compared to a standard ruler in the factory. Same with like a measuring tape or your volumetric flasks they use in the lab will have been calibrated using a known standard volume and then a line drawn on them. And so of course titration, you'll have your standardized titrant. Have you guys made any standardized titrants before? He's made, yeah, sodium hydroxide, then you weighed out the exact amount and you standardize HCl and then HCl titrate everything else, right? So yes, standardize something when trying to make some kind of comparison. Right, so your external standard analysis, and this could be anything on the instruments you guys will use. You can run this similar experiment or a similar comparison. You'll run a standard, so a preparation that you know what it is. So let's say we're analyzing caffeine. You will have taken a caffeine powder and made standards of a known concentration with your caffeine. And then you'll have your sample, which may contain unknown amounts of caffeine. So let's say we're doing the external standard to compare some tea leaves, right? You would take the caffeine, you would measure and make 5 standards, usually 5. In this case, we're going to be running the one comparison for our math today and for the midterm. But you'd have your standard, and then of course you'd have the tea leaves that you would grind up and you'd extract the caffeine and then measure the caffeine against your standard and do a comparison. HPLC is really good for this. So yes, you might have your standard, and of course you can do more than one standard at a time, and you can do more than one analyte at a time, as long as your peaks will dissolve. So yes, external standard is analysis by comparison. We can have standard or sample. You also might see it as, I always call it sample or unknown. People get confused when I mix those up for some reason. So yes, it's the most basic form of analysis, but it's one of the most reliable and helpful and useful, and one you guys are going to be using all of the time. So other standards might include the internal standard, and then of course standard addition, which you guys will be doing in instrumental. Are you guys in instrumental this semester? Instrumental 1, techniques in instrumental analysis. Yeah, so you guys will do that at the end of the semester. So yes, when we're dealing with the standards, we're calibrating our test. So when you set up your standards, you'll set up a low standard, and then you set up a high standard, and you'll have as many as you want in between. I've heard it mentioned you can do 1 or 2. I've heard you can mention you can do 3 standards, so 1 and then just do 10 times and then 100 times concentration, especially on ICP, I mean. You can usually, I'm used to doing 5. You have 5 standards, you set up a standard curve, and if you're getting a linear dynamic range, you should get a nice straight line like this on your curve or on a graph. If you measure the peak area versus concentration, you'll hear the term linear dynamic range a lot. Have you guys heard that before? Linear dynamic range. So essentially what that means is you'll have a certain range of concentration where you'll have a linear relationship between peak area and concentration. So it might not happen all the time. It usually doesn't happen if there's a very high concentration. It's usually more around the lower end. And if it gets too low, it might go along. But you'll get usually a period somewhere in there where you can measure things in a linear fashion. So if you make a sample that runs in there as well, you'll hopefully get your sample comparatively, will compare properly to that line. Let me just go with my camera setup. I need to share the screen for you guys. Sure, yes. Oh my God. It's been a long day, guys. All right, there we go. Share. Okay, there we go. You guys see it now? So, all right, does that make sense so far? We have a standard, we compare our sample to our standard. Yeah. All right. So this would be a multi-level calibration. So when you're making a standard curve, multiple lines or multiple standards would be made, 1, 2, 3, 4, 5, starting low and then going a bit higher. And if you have to make sure your sample falls within that range. So if your sample ends up, let's say on this one, we have peak area 500. If your peak area goes to 600, you either have to make a new standard that encompasses that higher sample concentration, because you're not sure if this is just suddenly go off on a weird tangent curve somewhere, or you need to dilute your sample a little bit. Diluting the sample, I think, tends to be a little easier, because all you have to do is just like dilute it by half, like take 1 ml, put it into 2, and then reanalyze it, and you're good. Making a new standard is a big pain in the butt, because you got to measure out some more caffeine, and you got to fill it up to the mark, and then you got to run it in the machine again. I find diluting the sample is easier. If your sample is too low, then you have to make another standard that fits under the curve for your sample, or you have to find a more concentrated sample, or because it all depends on how you're extracting your let's say your caffeine. If you're not getting enough, then you have to find a way to get that lower part of the curve encompassed in your standard, because you can't analyze anything reliably that isn't on your curve. That makes sense? So if it goes too low, this curve might suddenly just decide to go off in a random direction. So we know this part is linear, we have to stay within the linear portion of it. So our single level calibration, and that's what the basis of all our math today is going to be on. It's a single level calibration. We're going to be comparing to just one standard. So 2 points only. We're going to start with 0, and we're just going to go to a peak area. So we're going to be doing math that involves just that today and on the midterm. So we're not going to be doing any standard curves on the midterm, just single level calibrations. Right, team? The math is very similar. I almost find with this standard curves, it gets a bit easier, because all you have to do is know the equation of the line, and you can plug your concentration in or your peak area in and get it. But that'll come up later. Single level calibration. Start with 0, and we're just going to go to one standard. Now, most of the time, I believe on the next slide, they say, yes. So when are we going to use single level calibration? When our multi-level curve is probably going to be linear. You don't have to worry so much about making the 5 standards every time. As long as I go up to a certain level and I stay in my linear range that I know should be there, I should be okay to use single level calibration. And of course, we want them to be of a comparable magnitude. So I don't want to measure one that has a peak area of 500 and has a peak area of 7,000. You have to be within the same range. So 500, and then your caffeine peak for the sample might be like 520 or 530 or something like that. So we got to stay close. If you end up getting too far away, then you might have to do a bigger calibration. This helps you save time when you're trying to do the same analysis over and over and over again, especially if you know that you're going to be running the same samples. So if you're in pharmacy and using the same samples over and over and over again, it's not going to suddenly just shoot off in a random direction. You have a certain expectation for what you should see. Your quality control should be very consistent. Yes, so there's single level for quality control, and then you want your multi-level for environmental applications. Right, so depending on the variability of what you're looking for, let me see if I can switch over my cameras here. Oh no, they have the slides anyways. So if you know it's going to be consistent, you can use single level calibration. You probably would have done a multi-level one at the beginning and then made an SOP, and then the rest of the time it's just single level, and it saves everybody time. And then if you're doing environmental applications, measuring pollution, measuring lead in the groundwater, measuring mercury in the fish, whatever stuff like that, you would be using your multi-level calibration when you don't know where it's going to go. And you can handle this with HPLC, no problem. So yes, these are called external standard because we have samples and standards that are completely separate. The standard is external, which implies, of course, the internal standard, which will come in later. Yes. And of course, he says to make sure you don't mix up your calibration of your HPLC test, doing your standards with the actual performance verification, the plate count, right, the flow rate, stuff like that. We're not going to mix those things up. All right, so if we want to get a good result, we need 2 injections, standard and sample. We can also do more than one analyte, of course. Otherwise, the machine would take a long time to do anything useful. If we want to do single level, we should do 6 injections from our standard solution. We want to make sure we get a decent relative standard deviation between our points. We don't want the machine to measure one at 1,000 peak area, and another one at 500, and jumping back and forth. We want it to be consistent. So it measures 1,000, 1,001, 1,002, very small deviations. It shows the reliability of our machine and our software as part of our suitability assessment as well. And of course, it shows if your standard preparation was good, if you guys make good samples, if you guys are pipetting things properly, if you're rinsing things properly, it shows that you're getting good relative standard deviations. So yes, they might have a criteria of percent RSD not more than 0.1%. When I was working at Royal Canin, we had to measure toxins in it was pet food ingredients. And we did an external standard calibration, and we couldn't have an R-squared that was lower than 0.75. Put that on our curve. That was our requirement. Now, if you're in a big hurry, sometimes we tweak the color a little bit to see if the machine would read it as 0.8 or 0.9. Don't tell anybody. Because we knew that, we knew that the ingredients were fine, but you don't tell anybody that happened. Everything's fine. Just thanks to people into the waiting room here. Let's get a check on the Zoom friends. So chat. I'm trying to type 2 new messages. Can you share slides? Yes, yes, yes. Okay. Now, this is a formula that will come into play in the midterm 100%. All right. There's only a few formulas we have to really worry about. We just manipulate them a bunch for the midterm, for the math we're going to be doing. But because the area of the peak is proportional to the concentration of whatever component we're dealing with, we can run these ratios. So the area of our standard divided by the area of our unknown will be equal to the concentration of our standard and divided by the concentration of our unknown. So you usually know at least 3, well, we usually know 3 of the 4 of these, oh my gosh, my brain is not working. 3 of these 4 unknowns, and we should be able to find the 4th. And of course, this refers to a single analyte at a time. So caffeine on the bottom and top. You can't just compare caffeine to, acetaminophen or something, whatever we're doing. We have to make sure we're doing it one analyte at a time, depending on which one you're trying to check for. So this is our 4-corner equation, big one that we're going to be using. And we're going to be doing the math. There's a bunch of example questions in the lecture slides that we're going to do together. So we usually know 3 quantities, so we should be able to find the last one that we're looking for. And of course, this is for your single level calibration. If you're doing a multi-level calibration, you guys would measure all 5 of your standards. You would do the peak area versus the concentration, and then you get a line, a best fit, and you use the equation to find the concentration. We're not going to do that this time. We'll do that later on. So I want to ask you guys, do you want to do, so they have this whole thing about how to set up your chem station. Do you guys want to do that now before we do the example problems? Or do you guys want to do the example problems and then leave this to the end? What do you guys want to do? There's only how many slides left? You got a decent amount of slides left about this. What do you guys want to do?
Find the problems.
Do the problems first? Yeah, let's do some example problems first, and then we can jump into doing our chem station setup. Yeah. All right, team. Again, I find it really difficult to do this on lecture instead of just in front of the machine, but we'll zip through it later. So let's skip over to the example problems. Where did it go? Let's do one. Okay. So 8 word problems. Now it says 8 word problems, but it's actually lecture 8. Or set 8. It's only 4 problems, so it tricked me good, but okay. Okay, so here we go. And then let me write down the formulas we need. Where are they? Are they in here? Formulas we need are, here we go. So we're just gonna write these all down before we do anything. Formulas we need. We need the four, got my markers, I'm hoping these will work for me. So we need the four corner. So concentration. Oh no, the markers are dead. So I had markers all laid out. And of course I forgot. I'm so tired. Ah, come on. That's fine. I have markers laid out. Markers, where are you? Ah. Oh yeah, I got one. Oh, another Sharpie? Oh, cool, thanks. Beautiful. All right. 10 points to Gryffindor. All right. So concentration of, oh, it's a good one, of the sample divided by the concentration of the standard is equal to absorbance of the sample of the absorbance. Absorbance of the standard. You guys on Zoom see it okay? If you guys on Zoom can't see those equations, just write them down, okay? Concentration. Now we're dealing with milligrams per milliliter concentrations a lot. So we're gonna be just doing everything in milligrams per milliliter. If you have to convert to molarity, we can do that later on. What we're gonna do, it's gonna be weight divided by the volume. So weight in milligrams, volume in milliliters. And then if we want to do the conversion or weight, I always like to have the rearrangements available so my brain power can be spent on other things. So concentration times volume be the weight in milligrams, of course. Then if we're doing multiple dilutions, concentration will be equal to the weight over the first volume. So the initial dilution you're going to do times whatever volume you're putting into the second dilution. So let's say I'm putting 1 milligram into 10 mils. And then I'm going to take 2 mils of that and dilute it again to another 10 mils. That's V2 over V3. So let's say it'd be V2 over V3. So I'm going 10 milligrams, 10 mils, 2 mils into another 50 mils, right? And et cetera, et cetera. So as we travel down the line, however dilutions we're doing, we just multiply by dilution factors. Have you guys done dilution factors in microbiology yet? Are you guys gonna have microbiology?
We don't have micro, but we've touched dilution factors.
Yeah, so dilution factors, this is essentially what that is, right? So I'm doing a 1/10 dilution, it's 1 over 10. If I'm doing a 1 over 100 dilution, it's 1 divided by 100, right? So my concentration gets diminished as we go. So the way we show this in math is it's Vn, or I guess, you know what? The proper way I'd show that would be dot, 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 you know, Vn over Vn plus 1. Right, so however many dilutions I'm going to be doing, and then the weight, if I want to find the initial weight at the end, I have to reverse this. I have to flip it over and bring it back. So you guys will notice on the other equation, it's concentration times V1, but then we flip it over, it's times V3 over V2. And then it'd be V4 divided, no. Yes, I think so. No, 5 over 4. There we go. So if I want to go back from my concentration, back to my original weight, I have to take my dilutions and flip them over and bring it back to the original weight. So it comes back and it flips these over. So I have to take my initial dilution factor and I have to multiply by the inversion of it, right? So let's say I have 10 milligrams and I dilute it by 100, I have to multiply by 100 at this point to bring it back up to whatever it was initially, right? And then our percent purity is going to be the weight by HPLC. Put this over here. Percent purity is going to be whatever my HPLC says I have. Weight by HPLC. LC divided by the weight that is on my balance. And then finally, percent label claim is gonna be percent label claim. You guys see this okay over there? Kind of a weird angle. Percent label claim is gonna be the weight of the dose by HPLC divided by the weight claimed on the label. Claimed on label. So let's say you do an analysis to find how much Tylenol or how much acetaminophen is in a pill, and you get 355 milligrams, and the pill says in each pill is 350 milligrams. This is how you'd find your percent label claim. So a lot of places will say we have to be within 90 to 110% of whatever our label says we have to pass QC. And so you do that to find the percent label claim. All right, so I always find it's much easier to use these kinds of equations in actual practice. So let's go to that first question, which is up here a little bit. And there'll be a couple of rules we have to remember. I will be very flexible on these rules, okay? For me, all I really care about is this is going to be an on-paper test, okay? I want you to get in the ballpark of the answer. That's my main thing. And then everything else will be like sprinkled on top, okay? But let's start with this first question and see if we can puzzle it out, how to get the final answer without having to jump to the answer yet, because the answer is on the next slide. So let's take a few minutes on the actual question. So you're doing HPLC, we're looking for an ingredient. Our standard solution has 0.0205 milligrams per milliliter. And then we have peak areas. Our standard is 872.929, and our sample is 998.498 units. You guys will find that peak areas tend to just be listed in units. It's not really, it's almost like, they just like cancel out so you can get your milligrams later. And the conditions were the same. All right, so we have all the things we need except for the concentration of the sample. So we're gonna have to isolate the concentration of the sample there. This might be better if I can like draw on. I also did all these questions yesterday to make sure I was good. A few minutes, that question, simple rearrangement, cross multiplication shouldn't be a problem. Oh yes, and I forgot. There are some rules we have to follow to report our unknowns. So rules, when you guys are moving down, bring all the decimals with you before you do the final. So don't round things in between. All right, so write down whatever your calculator gives you. I like to just leave it on the screen and just punch in the next calculation, right? So don't round things before the end, right? But we have to round the final result to the same precision as the precision of the balance or the acceptance criteria. So let's go up here. So for this one, I think we have to say 4 decimal places. So whatever precision we're given, we have to go to the concentration of the standard. We have to report the sample at the same concentration level. This is kind of just like a sig fig problem at this point. But these come in later. Formulas. All right. Do we have any final answers? That one? Ease into it. Units should end up being milligrams per milliliter. It's like friends. Dear friends. Oh, oops. Uh-oh, what happened? Oh, more people trying to get in. All right, do we have a final answer? Everybody got one? All right, so I got Kamel in me. I will definitely talk about the midterm checklist and topics, I promise. So the correct answer, you guys want to still work a bit, or you want me to just give you the answer? Who's still working, wants me to shut up? Okay. Um,
Go ahead.
Tell Camille his answer is right or not. You guys can't see the chat. Yeah, I don't know about you guys, but whenever I have equations for a test, I like to rearrange them in all their possible iterations, so I don't have to worry about it later. Especially anything to do with trigonometry, sine, cosine, blah, blah, blah. I like to have them all laid out, all possible iterations of the same equation without having to arrange it on the fly, you know? Okay, good, good. Who's still working and wants me to be quiet for a minute longer? All right, you know what, I'll give you guys till 8:35, one more minute, okay? Because if we're gonna take this long on this kind of calculation, it take a long time for the other ones. But one little spicy bite at a time, okay? I don't know about you guys, but when things get down to actual math and formulas, I find myself much more comfortable, right? Because then it's like, okay, I just have to plug things in, right? Okay. Need a word. Right. We have to. My phone. Someone's texting me. Okay, so let's switch to the answer slide. So zoom down. Okay, so there is our calculation. So you would isolate for the concentration of the sample. It'd be the concentration of the standard times the area of the sample. So you just multiply up here, right? Divided by area of the standard. And you should end up with 0.0234 milligrams per milliliter. So it should be 0.0205 times 98.498 divided by 872.929. Cool so far? Yeah. Simple rearrangement. Okay. Let's jump to the next one. Problem 2. All right, same thing. Now we're back to caffeine. So we have caffeine test. Now we're doing serial dilution. So now this is going to involve this equation with the dilutions. Dot, dot, dot. And yes. Rotation is terrible. Okay, so we took our standard, 37.2 milligrams. We put it into 10 mils. And then we took 2 mils of that and put it into another 10 mils. And then they did 1 mil into another 10. So 3 steps. So if you'll notice, V1 will be 10 mils, right? V2 will be 2 mils. V3 will be 10. V4 will be 1, and then V5 will be 10. Right? So we're doing our dilutions down the line. So it's a 10, 2 to 10 dilution, then a 1 and 10 dilution. So you guys might ask, why do we bother diluting? Right? What's the point? right? So why don't I just go straight to that lowest dilution? Like take a tiny amount of caffeine and put it into 10 mils, right? Sometimes it's easier to measure something that's at like 37.2 milligrams is still a pretty small number to measure, especially on a balance. If you're trying to get this, whatever this concentration is at the very end, it'd be really hard to measure that manually. So you dilute bigger volumes from a concentration you've already made. So it'd be a stock, a substock, and then another substock. In our test sample, 26.1 milligrams of our mixture. We do two-step dilution with that. Then we get our areas of our curve. Ah, there you go. Okay, you got it. So work this problem out. Everybody know where to start, do you think? Yeah. Okay. All right, I'll give you guys 5 minutes before I bother you again, okay? Okay. Camera. The final answer you're saying, Kamel? Kamel? The final weight. So you're halfway there, Kamel. Remember, because the final answer is we want how much caffeine is in this the final sampling, right? But I also think that's wrong, fortunately. Racer. Two. Wait. 39. Backwards. I have it backwards. 128. 0.39. Okay. That comes out to what? Concentration of my sample. Yes. So Camille, you can do it that way, or you can plug it all into the bigger equation, the four corners equation. Four corners, this guy. Oh wait, can't see it. Can't see it. All right. That comes out to 0.180 16759. Gotta keep all those decimals. That's why I just kind of leave it on the calculator and leave it alone. This is milligrams per milliliter. That's my concentration of my sample. Machine. Right. Everybody get a similar answer? Similar. All right, what do I do next? What's my next plan? What do I do next? Because I'm not the final answer yet. I have the concentration in the actual machine.
Oh, yeah.
What do I do after this?
Count for the dilution.
Yes, we have to move backwards in that dilution factor, so we're gonna have to use this guy. Right? So C1V1, but we have to flip over our concentrations. So you have to make sure you remember which volumes are what, or just invert the dilution factors down the line. Right? So it's gonna be the weight is going to be so C being this one. Right? So the concentration we got over here. I want to write that down again. Sure, 180. This is why I think the 8759 milligrams per milliliter times the first volume, which was 10 mils. No, wait. Yeah, 10 mils. 10 mils. And then we have to flip over the next dilution. So it was 10 over, it was 1 into 10. So I just put it as 10 over 1. Multiplied by 10. So it's going to be times another 10 mils over a 1 mil. And that should give me what, 100 multiplication. So just this with the decimal point moved over 2 points. So 18.0168759 milligrams. And the milliliters should all cancel out. You should end up with, yeah, a nice sample or a nice concentration. So that's okay. So there we go. That's just the math I already did on the board. And then we end up there. So injected sample concentration, right? Let's tell if my friend's online to see. Can I zoom out? Zoom out? Oh, I can zoom out. Look at that. The camera's watching you guys on the back there. All right. And then on to the next one. And then we get our 18 at the end. All right, so we have to multiply by our dilution factor to get our original sample. Now, does it continue a little further? Yeah. Now, let's look at the rule here. Rules dictate we have to make sure we round our final result to the same category, the same precision as the given. So we were given in the original sample, it was 37.2 milligrams of the original sample. Right, so we get two, where is it? 37.2 milligrams is my standard. So I have to, and also in my original sample was 1 milligram or 1 decimal point as well. So we have to round our final answer to the one decimal point. So 18.0. That's what it rounds down to. So I might make that like final standard deviation or the final figuring things out. I might make that worth like 0.5 points. I'll make the actual math worth all the points, most of the points. And then you guys figuring out what your final declaration should be will be like half a point. Okay. So because I measured my sample as 1 decimal place, I have to put my final answer is 1 decimal place to the balance of the lab. All right, so there we go. That's the second one. Now, is that the? Oh yeah, so there's a way you can skip a bunch of things. Find that a little bit. Yeah. Where was it? I wanted to expand this one a little bit. That's fine. We can just. So it kind of goes on to point out that if you notice that a bunch of these milliliters are 10, you can cancel them out. That's all well and good. If you can notice it, you can do a bunch of cancellations and skip a bunch of the math. Good on you if you can figure that. If you can find stuff like that. I find it won't be like that a lot, but if you do find that things will cancel out, if you're really good at math, you can see these things and point them out. I would not be able to discover this just by looking at it. I'd just be like, I'm just gonna do the math, I'm gonna power my way through and then get to the line answer. So but yes. All right. So are we okay with that question? We all right with it? Yeah? Does anybody needs like a little bit more further explanation? Are we doing okay? And there will be more homework problems that I will post that actually come from the machine. So we can deal with that. Okay, let's zip to the next one. Okay, so doing the same thing, doing some HPLC analysis. We have our sample, we have a product measuring with HPLC. So we're gonna have a purity question. We have to be able to get our sample measured, and then it has to come through 99% purity to pass QC. We made their standard by 50.12 milligrams of reference in 100 mils. And then they had an HPLC peak of 501.2 units. And then our test sample was our product dissolved in 200 mils, and our area was 6. So we have to do the exact same thing we just did in the past two questions, but now we're going to do a purity calculation. So using our percent purity balancer. Let's get all this. In. 5 minutes before I bother you again. 3 minutes. 3, 4, 2. Got it right, Camille. Yeah. Okay, so. Anybody got a percent purity yet? We got 98.6. All right, so let's look at this final, let's look at the rule. Remember, the rule is when you're reporting the purity, you have to do the same decimal points as what they're asking. So 99%. So you had 98.6. If I were to round that to no decimal points, what would it be? 99. So does it pass? Yes. So there's going to be a question on the test. There's a couple of them exactly like this. looking for this kind of nuance. The test itself, yeah, passes. So the test itself is just gonna be calculation questions exactly like these ones. So it's gonna be what 3 or 4 calculation questions exactly like this. And then it's gonna be like a couple, there's a couple of true, is a true or false, right? Can HPLC do this? Can HPLC do this? Right? Can I measure this with HPLC? Can I measure this with HPLC? Stuff like that. And then, so just check my little topic list here. Yeah. The midterm itself is basically just on this type of calculation and just really, really basic knowledge of what HPLC can do.
Is there any essay questions? No.
Not in a chem course. No, thank you.
Alright, well, the formulas for the plate counts, you said you're gonna give us that, right?
Formula for the plate count, you won't even need them. No questions about plate count.
Oh,
No questions about plate count.
thank you.
No plate count questions on the midterm.
Thank you.
Won't even need them. All right. So, yeah,
The question says peak area, does that always just mean absorbance units?
yes. Absorbance units, sometimes it's in things called intensity, sometimes it's in MAU, like milli absorbance units. So it could be like tiny bits because it's a very small signal. But as long as you're using the same conditions, it should always be a useful number, as long as you're not changing big conditions. There's all sorts of different things you might find on the axis, especially if it's like a fluorescence detector. It might have, I think it's in intensity units, which can be like many thousands, but it'll always be a useful number you can use. So in our case, it's always going to be units.
If it's like in like intensity or something like that, do we need to convert it or do we just use that?
Intensity is basically just like another word for absorbance.
So we just use that number?
Yeah, so I'm not going to give you any questions that involve intensity. No. Just be units. It'll be straightforward, easy to do. Yeah.
If the volumes are the same.
If the volumes are the same,
The standard was made with 100 mils and then.
Right.
This, do you have to show that step?
as long as the math works out, and you can cancel things out. Like in that previous one where he was showing that the volumes were all the same in a bunch of different places. So he was able to cancel a bunch of them out. Right? So they did some 2/10 dilutions. They did a 1/10 dilution for the sample as well. So yes, they might cancel out. For me, I'm too paranoid to do that. They're asking me a question. I'm just like, I put everything in. I'm not gonna try and be smart and cancel anything out because I know I'm gonna screw something up and then I'll get the wrong answer. So, yeah. So the previous topics, guys, we're not gonna worry about at all. It's just gonna be these kinds of calculations and very basic, what can HPLC do type of questions. And then the purity calculation. So, would I say if a purity falls in this range, what would I report it as? Right, or if I get a percent purity of this, can I say it passes or based on this criteria? All right, so it'll all be this external standard, very basic stuff, okay? We're on question 3 still. So let's zip over. So we didn't finish this question yet. So first, we get our concentration of our standards. We have to dissolve our standard into 100 mils. Then we have to do our formula to determine the concentration of the sample. So we end up with 0.5436. Then we have to do our dilution, get back to our original sample. So we end up with 54.36 milligrams of weight that we put out. And then we have to find the purity. The weight that I determined on the HPLC, that would be 54.36. Where is it? Divided by what the weight of the sample was, which was 55.13. And we end up with 98.6. And then if I look at the purity regulation they gave us, minimum 99%, I round to whatever that precision is. So no decimal points in my calculation. So I have to round up to 99, so it does pass. I put that on the board if you guys want. So it's 54.36. Divided by 5.13. So to 98.6, which I have to round to 99. Be okay with that question? Now, in terms of equations for this. I think I'll give you the equations, but I'm not gonna label them. So you have to be able to recognize the equations, okay? You have to recognize what they are. As long as you're not gonna be like, this is the purity equation, you know what I mean? Although, you know, it's hard to write an equation that doesn't have like purity in it, but stuff like this, you have to know these terms, okay? Last problem. Okay, so there's the rule. So we have to the acceptance criteria, same decimal points. Everybody's leaving my online thing. There's only 3 people left. Yes. Okay. Go, and finally, our percent label claim equation or question. So we have our product, we have our tablets, right? Our tablet says it's a 350 milligram tablet. In order to pass each QC, it has to be within 90 to 110% of what that label says. So we determined the average tablet weight is 900.33 milligrams. You guys will find this a lot. If you're measuring anything that's in a tablet form, the tablets themselves have a little bit of variability in their weight. So take like 10 tablets, you'll crush them together, right? Or you'll weigh 10 tablets at once and divide it by 10 to get a bit of an average. And then you'll crush the 10 tablets and you'll take a small sample of all 10, so you get a nice mixture of everything. Right, so that you're not just taking one tablet out of the whole bunch and saying this is representative of the whole thing. You take a nice big sample and take a little bit out of that to measure with. So yes, the average tablet weight is 900.33 milligrams. Again, they probably took about 10 tablets, measured all 10, and then divided it by 10. We have our standard, our pure pharmaceutical active ingredient. I hate when they say that. It's like, why don't we just pick an ingredient? Why don't we just say it's a acetaminophen tablet or whatever. Pure pharmaceutical active ingredient. So we took our standard, we took 50.15 milligrams, dissolved it into 100 mil, and we did our chromatogram. We got 600.6 units. And then they did their tablets, took 154 milligrams of that, dissolved it into 100 mils. And then we get a peak area of 700.7. So you have to find the concentration, then the percent label claim. You're gonna have to go percent concentration, then you're gonna have to go to weight. And then you're gonna have to go to percent label claim. Bother you 5 minutes. Okay. Yeah.
One question. The part where they said equal to 600.6 units, what does the unit means?
That's just your absorbance units.
Oh, okay.
Yeah, so just whatever the peak on the graph is, wherever it reaches, or the area, sorry, the area underneath the curve when they integrate it is that many units.
Okay.
And after. Other units. So. Here we go. So. All right, so we're gonna calculate the concentration of our standard. 50.15 milligrams, 100. Then we're going to get our sample. Comes out to, we rearrange the formula, we come out to 0.585. 0.83 milligrams per milliliter. And then we know we did how much dilution? We did 100 ml dilution, so we have to multiply by 100. And we end up with 58.5083 milligrams. And that was in our sample. All right, so let's take it from here a bit manually, right? So 58, everybody in the camera see me? Yes, 58.5083 milligrams. That was in what sample? How much was it in? It was 154.32 milligrams, right? Where am I? Yeah. 154.32 milligrams of sample. Now, what does that come out to? 30 something percent? Something like that? Let's check it out. So there's a couple ways you could do this mathematically. 503 divided by 154.32. We'll have 37%. This is how I did it. 37.9%. Right? So what I did was I took my sample weight or my tablet weight, my average tablet weight, multiplied it by that number, and I see how much milligrams I get. Right? So my tablet weight, if I go up to it, go to my tablet weight. My tablet weight is 900.33 milligrams, right? 900.33 milligrams, right? I might get 37% of that. 33, is it 33? Yeah, I get 341 milligrams of my active ingredient. It's in one tablet. Does that make sense? Because in this small sample, I have 37.9% of my ingredient. So in my full tablet, it would be 341. You can show this mathematically if you want. You could do this over this equals X over 900 if you want. So you can do equals however much is in one tablet over the average weight of the tablet. 3 milligrams. That number would come out to 341 milligrams, just about. Milligrams. And so my percent label claim, I'll divide this by the weight claimed on the label, 350. What it says the tablet should have inside. And if I get a number between 90 and 110%, it is passing QC. Let's check it out. 341 divided by 350, get 97.5. Again, I have to multiply by 100%, right? 100 times this. 97.5. That shows how much is there. There we go. The 97.5 of the label claim is there. So it was between 90 and 110%. So this passes the QC. I want to see what the other guy had done. That same question. So then 50 milligrams. Yeah, so he looked for the same thing. So he did a ratio a different way. Weight of the power of the tablet over the weight of the average tablet. But you end up with the same number in the end. And then you divide that by your number. And you should get, 341 divided by 350 and about 97.5% within the limits. So we passed. So it's a little bit counterintuitive, a little bit convoluted to find the right number, right? But you just have to, keep your head in the game and get there and get to that final calculation. All right. Lovely. Okay, so that was the last problem, I think. In the worked problems there. And then we have to just remember the formulas. And then you have to remember the rules. Now, there's one thing that isn't touched on here, which we have to make sure we touch on, is the average peak area. So if you're given multiple peak areas, right? So multiple peak areas, write this down somewhere. So multiple, very closer to this side, so you guys can see it too. Oh, where do I put it? So multiple peak areas. Multiple peak areas. All right, you have to take the average. The average as your standard peak area. Okay. So if you're given a peak area 900, 901, 903, take the average of those, and then that will be the area of your standard. Okay. So the exact same kind of math, you'll just do it with an average of a bunch of different ones at once. And then you might also have multiple samples as well. Just get the average. Most of the time you would run like at least a triplicate of your sample. You wouldn't just run like sometimes they run up to like 10, right? So you do it a bunch of times. You have an auto sampler for that, of course. Yeah. And then anything else? Yes, that's all of that. Okay, now there are two more problems in the that have actual data or actual HPLC data we can use. So we can do these two as well. All right, so here we have what your data might actually look like. So we have an HPL test as liquid sample, look for two ingredients for a standard solution with the respective ingredients. And the individual chem station reports are reproduced below. So we have our peaks. Here's our standard. So you have two standards, two peaks. So you have a retention time. So that's how you match the peaks to each other. And then your amount and your areas. And then don't worry about the rest. All right, don't worry about the rest of these amounts over area. Not gonna worry about that. All right, so use those numbers for your standards. And then at the bottom, they have the sample. So external standard analysis. And you'd have your retention time and your area. So you have all the information you could possibly want. And we're gonna find the concentration of the two ingredients in the sample. So we have our standard areas. You guys read that, you want to zoom in. Standard areas, retention times, and then your areas of your unknowns. Take 5 minutes for that one as well. Let's zoom in a bit. Sure. Okay. I'll give you here are the standards. And these are also on Blackboard if you guys want. There's your amounts and your areas.
What are we looking for?
So you're looking for, so this is your standard area counts. So you have your retention times, that's how you match your peaks together. Then you have your amount, so this is gonna be the concentration of the standard for each one, and then your area of each peak. So you use that in this formula, so area of the standard. And then each one is its own individual unknown. So it's one analyte versus the other one. So these are, you have to do this calculation twice, because it's two different chemicals. So one would be maybe caffeine, and one would be Tylenol or acetaminophen. And then if you look down lower, we have the two signals that are in the sample. So we have the retention time, so you'd match the first peak to the retention time of the other one, and then the other peak matches. So if you look at it, this one has a retention time of half a minute. And then this standard signal also has a retention time of half a minute, so that matches that one. So this is the standard concentration, standard area, and then this is the sample area down here. And then you find your sample concentration. Make sense? And then you do the same thing for the other one in the curve. So you have this peak area for this standard, or this sample, I mean, retention time, and then you just match it to the other one. So I'm trying to get them all in the same view, but if I zoom out too far, we can't read it. So it's a bit of a tricky one. So we looked at the standards, let's look at the samples. I can also just write them down if you want. There are sample areas and retention times. So retention times don't matter in this case. All you care about is that each peak matches and you write down the areas. And when you report your final result, you have to make sure you write down the concentration, same as what the standard was calculated at. So it'd be how many decimal points? You get 5 decimal points.
So, when we're doing calculation, we're mostly focused on decimal points and not sig figs, right?
So whatever it kind of works out the same anyways, but yeah, you look for this decimal points of what knowns you have. So if I'm given the known to have 5 decimal points, then my unknown, I will report it with 5 decimal points. Unless they're asking for like a percent concentration, like maybe 1 decimal, I want it to 99.1 to 99.2%, then you report it to 1 decimal. Whatever their precision they're giving is, you match it. Yes, so these are the samples, and then the standards are up here. Cool. Okay. I do these ones manually. I did. Okay. Let's see. Who needs more time? Yes, more time? So first one is gonna be concentration of our standard. Right, samples concentration is the one we want. We'll rearrange our equation to find that one. Throw it in there. There's our formula. Oh, sorry. And we'll throw that in and we'll get our final answer. These equations are really, I don't want to clean them up a little bit. So sample concentration, 1.02995 milligrams per milliliter. Did we get that answer? Thumbs up. All right, next one. Second compound, same deal. Oh, okay, so he basically just says, we'll do the same thing. By analogy. You guys are smart enough to do the first one, you're smart enough to do the second one. All right. Beautiful. But there's the answer, 2.05417. You guys get that?
Yeah.
Love, okay. And then you can mess with that number however you please, right? With dilutions, if you need to calculate the percent this and the percent that. Okay, problem number 2, Excedrin tablets. The tablets that have acetaminophen and caffeine. Tablets, they say there are 325 milligrams. Minophen, oh my gosh, I've been up since 3:30. Acetaminophen and caffeine. And then they did the average weight, 0.4502 grams for a tablet. They crushed them up, took a portion, put it in a flask, and made some market improvement. And they made their standards. And we have our peaks. We have our weights. We have our concentrations. We go to and we have our chromatogram peaks. Sorry, okay. We have to get between 90 and 110% label claim. So it's 325 acetaminophen, 65 of caffeine. This is why you will like when the machine tells you things without you having to do the math yourself. Because let's say you do 3 or 4 analytes, it gets really annoying. Right, having to do this multiple times over and over and over again. Five minutes. 2 minutes before I bother you some more. Oh, look, the red one works. Right, I'm 35, I will bother you, there it is. All right, let's zip down to the final one. All right, oh, I could just give you the answer, so. All right, so the acetaminophen comes to 381 over 349, so 109%. ATW. Fine. Scale to ATW. I don't know what you mean by that. 109.1%, so it's a pass, and the caffeine comes to 60. Where? Comes to 89.2%, which is a fatal. When I write those ones out, so at least for one of them. Scale to ATW. That means scale to ATW. All right, well, let's do the one for the caffeine just for fun. So the concentration of the sample. Oops. Yeah, the standard. Sample. Times concentration standard. Divided by area of the standard. Concentration of the sample comes to area of the sample. Standard is 62 milligrams caffeine, 62 over 100. 100 mils. Area of the standard. Concentration of the sample comes out to. So 0.624. Or 806 milligrams. milliliter of the original sample. We have to multiply that by 100 to get to the amount. 100 give me the weights. 62 milligrams. 48 milligrams of caffeine in the 489 milligrams of the powder. 84. 9 milligrams of the powder. 12%. Not good, 12.88. Of that powder will be the caffeine, so multiply that by 325. 41.8. Am I losing it? Doesn't sound right. I'm lost in there somewhere. $12.88, that's what we want, 41.8 milligrams. One tablet. I don't know. I think I messed up a step there somewhere. What'd you guys get? You guys still working on it? Yeah, okay. See, right. So for my online friends, I have to stop the recording because I have to compile this recording before I can leave. So if you have any questions, let me know, but I do have to end the recording now, okay?